Hello, this is Mr. Boothman. I hope you all had a great fall break. I hope you're enjoying our first week back. Forgive me if I have a bit of a lisp in this video. I had some dental work done yesterday, so that's always fun. But today we are starting Unit 3, starting with 3.1, of course, exponential functions. This whole unit will talk about exponential functions and then logarithmic functions. Um, this is a really cool topic, especially because it has so many real world applications. So look forward to that as we delve into this in class. But for now, we're going to go through the basics. First, graphing exponential functions. An exponential function with base b is defined by f of x equals b to the x. So, just a really simple, straightforward definition of an exponential function. Base b is going to be important as we go through this unit. Base, keeping track of our bases. Just keep that organized. So we'll go through some examples of graphing exponential functions. As you might have guessed, they're just like other functions. We have an xy table and we plot the points. So here in A, f of x equals 2 to the x. So b equals 2. I'm getting this from here, b equals 2. So if I plug in negative 3 for x, that is 2 to the negative third power. Now if you remember our exponent rules, if I have a negative power, I can move it to the denominator of the fraction. So I have 1 over 2 to the third, which is 1 over 8. Same for negative 2. It'll be 1 over 4. Negative 1 is 1 half. If I plug in 0, 2 to the 0 power is 1. If I plug in 1, that's 2. Plug in 2, that's 4. If I plug in 3, that's 8. So if you're not as familiar with your powers of at least like 2 and 3 and 4 would be good too, I think you're going to get familiar with them this unit. So look forward to that. So let's go ahead and plot these points. Negative 3, 1 over 8. Negative 2, 1/4. Negative 1, 1 half. 0, 1. 2, 1. 2, I'm sorry, 1, 2. 2, 4. And then 3, 8. And then we connect our points. Unless you're me and you can't connect dots. So here's the graph of f of x equals 2 to the x. Our domain, do we have any domain restrictions for 2 to the x? We do not. Our domain is all real numbers. We can plug in any real number for x and it's going to give us an answer. What is our range? Well, you'll notice that if I plug in 0, I get 1. If I plug in anything less than 0, I get a fraction. If I plug in anything bigger than 0, I get a whole number. I'm never going to get 0. If you stop and think about that for a second, nothing I can plug in for x will give me 0. And I'm never going to get a negative number. There's no possible number for x that I can plug into this function that will give me a negative output. So my range is going to be y is greater than 0. And, as you might have guessed from this graph, I do have a horizontal asymptote at y equals 0. Again, because the range is y is greater than 0. I'll never actually reach 0. So this is an example of something we call exponential growth. And this occurs when b, our base, is greater than 1. So exponential growth should make sense. Our graph is moving up. Let's take a look at the next example then. F of x equals 1 half to the x. So here, b equals 1 half. If I plug in my points here, if I plug in negative 3 for x, I end up with the reciprocal, so that is 8. Plug in negative 2, I get 4. Negative 1, I get 2. 0 gives me 1 again. Plug in 1, I get 1 half, 1/4, and 1/8. So let's plot these points, -3 and 8, -2 and 4, -1 and 2, 0, 1, 1, 1/2, 2, 1/4, 3, 1/8. So this time my graph looks like this. My domain again is all real numbers. I can plug in anything for x. My range looks like it's the same. Y just has to be greater than 0. It will never be 0. It will never be a negative number. And then I have the same horizontal asymptote here at y equals 0, the x-axis. So the only thing that's changed here is that looks like my whole graph was reversed in some way. Before it was getting bigger, this time it's starting big and getting smaller. So this is an example of exponential decay. And this occurs when b is between 0 and 1. So when b is a fraction, less than 1. So basically, pause if you need to take a minute, but exponential growth, exponential decay, we're going to come back to this in our last section of this unit when we talk about real-world applications of exponential functions. But for now, as long as you're familiar with this and you know how to graph them, you should be good to go. So write down questions, make sure you bring those to class. We can also talk about transformations of exponential functions. Luckily, these are the same as before. You'll notice our letters are all the same. Our A out in front, that will create a vertical stretch or compression. If it's outside the parentheses, it affects y, and we do what it tells us. C, well, that's with x, that'll create a horizontal stretch or compression. But it's with x, it would be inside the parentheses, so it's lying. We do the opposite of what it tells us. H, here, that'll be horizontal shift. And again, it's inside the parentheses, so when we look at that shift, we'll do the opposite. And then K is a vertical shift. It's outside the parentheses, it is affecting y. We do what it tells us. Our reflections are the same. If we have a negative A, then it's a reflection over the x-axis. Oops. If we have a negative C, that's a reflection over the y-axis. So, none of that should have been new. Should feel pretty okay about that. It's just a different parent function this time. It's not like the rules of math suddenly change for exponents. It's great. So let's look at an example of graphing an exponential function beyond just our very basic. So what is the parent function for this f of x? Looks like it's going to be f of x equals 3 to the x. If we strip away all the transformations, that's what is our most basic function. Since b, our base, is 3, that's greater than 1, so this is growth. It's going to be really important for us to be able to differentiate between the two. And then this third step, we're going to use something called anchor points. And then we're going to look at the transformations. So this will make it super easy and simple for us to graph our exponential functions. Just follow along. I promise it's not that bad. So we're starting with just our general point. So for this function, I plug in an x, and I'll get out 3 to the x. So that's where these numbers are coming from. X, 3 to the x. Our anchor points for exponential functions are going to always be the same two. And then we'll change them according to our transformations. So we're starting with 0. If I plug in 0 to this exponential function, I get one, giving you time to process. Should be easy. If I plug in 1 to my parent function, I get 3. So this is an important point. You are plugging in, you are looking at the parent function for these 2 points here. Okay. You don't want to plug this into the transformed function because that'll defeat the purpose of everything we're about to do. So starting with this, we have our 2 points now. We call these anchor points. You will see this terminology throughout the unit. We are looking at our transformations, and we're looking at the order of operations. That's the order in which we do everything in math. That's the order in which we follow these transformations. So we're looking inside our parentheses. That would be everything grouped with x first. So I see x plus 3. That will be a shift 3 to the x plus 3. That's going to be 3 to the left. So that's affecting x. So that means I'm subtracting 3 from my x coordinates here. My new points are going to be negative 3, 1, negative 2, 3. So we kind of practiced this way back in section 1.4 in our first unit when we talked about transformations. But now we're actually going to use our tables because this is going to be so much easier than trying to do any other method to graph these. So you start with your 2 anchor points, then we'll fill out each of our transformations in turn, and we'll change the coordinates of our points for each step. So first it was a shift 3 to the left. That means I'm subtracting 3 from each of my x values in my points. Next I see this 2. That's a vertical stretch by a factor of 2. That means I multiply my y values by 2. It's affecting y. I multiply my y values by 2. Oh, sorry. It's not a 4. It's a 6. And then, final step, I have minus 4. That's down 4. I subtract 4 from my y values. And that's it. Those are my newly transformed anchor points. So I start with a parent function. I start with the same anchor points for every function. 0, and then whatever that ends up being. 1, and whatever that ends up being. Then I'm transforming those 2 points step by step as I follow my order of operations through my transformations. I start with what's inside the parentheses. I move my way out. Then I deal with multiplication, in this case any stretches or compressions, and then addition or subtraction, my vertical shifts. So step 4, determine a horizontal asymptote. This is going to be, now usually it would be y equals 0, but I just looked at my transformations. I'm shifting the entire graph down 4. So my new horizontal asymptote will be at y equals negative 4. I've moved down 4. And then, last step, I plot my anchor points and I sketch my horizontal asymptote and I fill in the curve. So let's do my horizontal asymptote first. Easy enough. Then I plot my 2 anchor points, negative 3, negative 2, negative 2, 2. And if you want to check this in a graphing calculator or Desmos or what have you, that's fine. I need to draw my smooth curve. So again, it's approaching the asymptote as it goes off to negative infinity, and then it's going up dramatically because it's exponential. All right. That was a really good example of how we do this process. If you need to pause this, if I lost you at any step, please take this opportunity to rewatch that part, to think through this with me, and then if you still have questions, write them down and bring them to class. There's only one last tiny part of this first section of the unit, and that is something called the natural exponential function. So I'm sure you've seen the letter that I'm about to write here. Exponential functions with base e are natural exponential functions. E is a constant in math. It's approximated by 2.71828, etc., etc., etc. E is like pi. It is irrational. It is non-repeating. It is a transcendental number. We can talk about transcendental numbers a bit in class. But this is where we use E. I'm sure you're wondering where E comes from, and I do have an answer for you, but I don't want to spoil it in this video. I think we're going to save that for class. We can explore that together and try to come up with E ourselves. But for now, this is what E is, and it works the same way as all our other exponential functions. So since E is 2.71828, that's greater than 1, this is an exponential growth function. And then we can graph this the same way that we graphed all our other exponential functions. So in this case, f of x equals e to the x. So as I plug in my x's, I'm going to get values. I'll have to use a calculator for e. But if I plug in -3, I'll get 0.05. If I plug in -2, I'll get 0.14, 0.37, 1, 2.72, 7.39, and 20.01-ish. And then I could go on ahead and graph that. So, very, very basic overview of the natural exponential function. We are going to talk so much more about this throughout the unit, but for now, I wanted to introduce the notation and get you thinking about this particular function. So that's it for 3.1, exponential functions. I'm really excited for this unit. I think it's going to be a great unit, a great quarter. Bring your questions to me and Miss Parker, but otherwise, have a fantastic day.